Are you looking to push your custom accelerator block to faster clock rates for even higher performance? If so, you have come to the right place. Part of the Advanced Technique tutorial series by Alorium Technology, this video focuses on using custom clocks with our OpenXLR8 methodology. Your host for the presentation is Steve Phillips, lead design engineer for the Xcelerator platform. Let's jump into it.
Hello and welcome to our Alorium Technology tutorial on using custom clocks in the OpenXLR8 flow. Today we're going to go over a number of topics. First, we'll have a quick introduction to Xcelerator in the OpenXLR8 flow. Then we'll discuss how clocks are generated and used in OpenXLR8. And then we'll have an example of using custom clocks in our OpenXLR8 flow. We assume for the purposes of this tutorial that you're already familiar with the Xcelerator and OpenXLR8 flow. If you're not, please go and watch our Intro to OpenXLR8 webinar available on our YouTube channel at this link here. Additionally, if you're going to walk through our example with us with your own Xcelerator board, you'll need a laptop with Windows or Linux, and then you'll need the Arduino toolset as well as the Intel Quartus Prime toolset to run our OpenXLR8 flow. And finally, you'll need a USB mini cable to connect your Xcelerator board to your laptop. Here we see an overview of what's inside the FPGA chip that's on your Xcelerator board. In the gray box, we have our AVR processor and the peripherals attached to it. Next to that, we have a reconfiguration block that allows us to change the image of the FPGA using the Arduino IDE. There's a PLL that's used to generate clocks. And finally, the remainder of the FPGA is used for our Xcelerator blocks. Xcelerator blocks are custom hardware that are implemented either by Alorium or by the user using the OpenXLR8 flow. They're tightly integrated with the microcontroller, able to actually access the same register space and the data bus of the AVR itself. Alorium provides a number of predefined XBs that are available on our GitHub or through the Arduino IDE. And we're always adding more. Briefly, the OpenXLR8 flow allows the user to add custom logic to their FPGA on the Xcelerator board by writing HDL code in either Verilog or VHDL, and then using the Quartus Prime tool to generate a new image for the FPGA. Then we have custom scripts written that allow you to load that image through the standard Arduino IDE onto the Xcelerator board. Once that new image is on the board, we can run sketches on the board using the Arduino IDE. Now let's talk a little bit about clocks and their use on Xcelerator and OpenXLR8. Clocks for the Xcelerator are generated using the Alt PLL IP core from Intel. This implements a phase lock loop, which is a standard way of generating clocks for use within FPGAs or ASICs, which are custom ICs. Using the PLL, it's possible to generate additional clocks that are running at a different rate or frequency and different phases relative to the reference clock that comes into the chip. The phase of these internal clocks are locked to the phase of the external reference clock. To learn more about this IP core, you can go to the user guide available on the Altera website at the link shown here. The PLL that's used in the Xcelerator is configured as shown here. The in clock 0 signal coming in is our reference clock, and from that we're generating 5 additional clocks. C0 is the 2 megahertz clock used for ADC logic, and then we're generating 2 64 megahertz clocks, one of which has a 45 degrees phase shift, and 2 32 megahertz clocks, one of which has a 22.5 degree phase shift. These are output from the PLL as signals C0 through C4. That PLL is then instantiated inside of our Xcelerator clocks module. This wrapper logic does some selection of clocks for use within the design. The clock signal coming into the left side is our reference clock coming into the chip. And then the clock CPU coming out the right side is the CPU clock that's used in the AVR core. Depending on the configuration that you're running, it selects either the 16, 32, or 64 megahertz clocks that are generated inside. We also export the clocks that are coming directly out of the PLL for use in other logic. The clock ADC ref is the 2 megahertz clock used for ADC. We export the 16, 32, and 64 megahertz clocks, as well as clock option 2 and clock option 4, which correspond to the C2 and C4 outputs of the PLL. These clocks are then used as custom clocks in the OpenXLR8 module. These are the ones that we'll be modifying for use within there. The normal use of the Quartus, we use their Mega Wizard to configure the PLL. You can specify your desired clock frequency either directly by entering the clock frequency, or you can specify a multiplication and division factor directly. The phase shift can be specified in either degrees or in nanoseconds, and the duty cycle can be specified as well. Once the Mega Wizard has built the PLL and its configuration files, it's possible to edit those configuration files directly to change those values that we entered in the Mega Wizard. But rather than require the user to dig through the PLL configuration files to do that, the OpenXLR8 flow includes a file to do it for you. The PLL16.vh file lives in the extras/RTL directory, along with all the other OpenXLR8 files that you'll need for the OpenXLR8 flow. This is the key file for using custom clocks in OpenXLR8. By simply modifying the values in this file, we can create custom clocks that are then available for use within OpenXLR8. As I mentioned earlier, there's 2 different clocks that we can modify, clock option 2 and clock option 4. And those are shown here as Xcelerator PLL clock 2 and Xcelerator PLL clock 4. You can see the 4 different values that are specified for each of those clocks. By modifying the values listed here, you can create a custom clock. The values we show here are the default values that are used in Xcelerator, but you can change these values to create your own custom clocks. To come up with values for those configuration parameters, we need to understand how they're used. For setting the frequency of the clock, the divide by and multiply by settings are used. These are always relative to the reference clock coming into the chip, which in the case of Xcelerator is always 16 megahertz. So the clock output frequency is going to be determined by multiplying 16 megahertz times the ratio of multiply over divide. To get the clock output you desire, you may have to do some trial and error to come up with values for multiply and divide that get you close to the value you want. Usually it's possible to find values that get you within 0.1 or 0.2 of the desired frequencies. The duty cycle parameter is an integer value between 0 and 100. The typical value is 50, which is a 50% duty cycle, resulting in a clock signal that's high half the clock and low for the other half. Using this value is useful if you need to move the falling edge of the clock relative to the rising edge of the clock. And finally, the phase shift value is specified as a delay in picoseconds. This is the delay that will be applied to the custom clock relative to the reference clock. If your phase shift parameter is specified in degrees rather than picoseconds, we need to convert that degrees into picoseconds. The equation shown in the middle of the page here shows what that equation is. Clock output frequency in this case is our target output clock frequency for our custom clock, and then phase shift in degrees is the desired phase shift. So for example, we want to create a 256 megahertz output clock with a 45 degrees phase shift. We would use the equation as shown here. You can see the 256 by times 10 to the 6 is our 256 megahertz output clock, and 45 is input as well. Calculating out that equation, we come up with 488 picoseconds as our phase shift, and that would be the value that we would enter in for phase shift. Now let's walk through a simple example of using a custom clock within OpenXLR8. Here we see an overview of the FPGA and what's inside it for our example. On the left, we have our AVR core, which is the Atmel compatible microcontroller inside of the FPGA. And on the right, we have our OpenXLR8 module. Inside of that module, we're going to instantiate our clock option example. inside of which we're going to create two counters, one of which runs at the normal clock rate and the other that runs at our custom clock rate. So we'll be able to run those counters in parallel and then look at the counter values to determine if the ratio between those two counters matches the ratios of the clocks. The counters are fairly simple. There's two clocks that come into the module. Clock option is our custom clock, and clock CPU is the CPU clock. So that's at 16 megahertz. Our run signal controls the counter. Since that is on the CPU clock domain coming in, we run it through a couple of flip-flops to synchronize it to the clock option domain. And then we look at the edge of that run signal to determine what we need to do. In the counter, we have two inputs, a clear and an increment. If we see a rising edge on the run signal, we know that we want to start counting, so then we clear the counter to start at 0. As long as the run signal is high, we're going to increment, meaning that for every clock, in this case, our custom clock option, for every clock, we were going to increment the counter. When we see a falling edge on the run signal, we know we're going to stop running. We run that stop running signal through a couple of flip-flops to synchronize it back to the standard CPU clock domain and export that as our stop signal. We also export the counter value, which is a 32-bit count. Going one level up in our example, we see we have two counters instantiated. Example counter 1 uses the CPU clock for both clock CPU and clock option, meaning that the counter inside of there will be running at the standard CPU clock rate of 16 megahertz. In the other counter, we're using the clock option 2 as our clock option, meaning that the counter inside of this counter will be running at our custom clock rate. To control those two counters, we have some configuration registers. The control register contains some status bits as well as the run signal. Bit 0 of the control register is used to control the run signal for both counters so that the two counters are stopped and started synchronously with each other. For each counter, there is a data register that allows us to read the counter value. Since the counter is 4 bytes wide, 32 bits, and the data register is only 1 byte wide, the dbus interface logic contains some control logic that will allow us to read bytes out of the counter value one at a time. By doing 4 sequential reads of a data register, we'll read all 4 values from the counter. Here we see a definition of our registers being used. Accelerate clock control is at address 0FD in our register space. We see bit 0 is our run signal, which is a read-write value. And then we have several bits here of status. For each counter, there's a stopped bit and an overflow bit that indicate the status of the counters. Then we have 2 data registers, data clock and data clock 2, one at address FE and the other at address FF. Each of those will return 8 bits at a time of counter data. Finally, we're going to instantiate our clock option example inside of the OpenXLR8.v module. Here we can see that our clock option 2 is using the clock option 2 signal coming into OpenXLR8. So what is clock option 2? Well, this is where we're going to edit our PLL 16.vh file to specify what we want to use. In this case, we're going to create a 128 megahertz clock with 0 phase shift. To do that, we'll set our multiply by value to 8 and the divide by value to 1, resulting in a value of 128 megahertz generated from the 16 megahertz reference clock. We're going to set our duty cycle to 50 by setting that to 50%, and we're going to set the phase shift to 0. And that's all it's really needed to do to create a custom clock. Now we're going to build our image using the OpenXLR8 flow and the Quartus toolset, and then load that image onto the Xcelerator board. With our image on the board, we can now run a test to see how that works. First, we've developed a simple accelerate_clock.h file that first specifies to the software the addresses of our control registers, FD, FE, and FF, as we saw earlier. And then it creates a class with some functions that allow us to communicate with our registers. There's a run counters and stop counters function that allow us to start and stop the counters. A get status function that will read the control register to get the status bits. And then for each data register, there's an initialize data clock and read data clock function. Initialize data clock resets the state machine for reading the counter value, and then the read data reads 8 bits at a time from the counter value. And then to put it all together, we've got our accelerate_clock.ino sketch that goes through and exercises the two counters. First, we call run counters to start the counters. Then we run for 100 milliseconds to let the counters increment, and then we stop the counters. Next, we read the counter values back by first calling initialize data clock, and then doing 4 reads of the data clock and assembling our 32-bit counter value. We do that for both of the counters to get both counter values, and we print those out. Then we calculate the ratio of those two counters, and hopefully the value we get is the ratio we expect of the two clocks. Running the sketch results in the following output. We see the counters are started and then they're stopped. We get our counter values, which are printed out here. And calculating the ratio of those two, we get a ratio of 8, which is the ratio we expect of the 128 megahertz custom clock to the 16 megahertz CPU clock. Thank you for joining us today for a tutorial on using clocks. Please visit our website to learn more about Xcelerate and Snow, as well as the OpenXLR8 flow that works on both of those boards. We also have a YouTube channel that contains many more videos. And as always, our support is available at support@AloriumTech.com. Thank you.